All right. So originally I did plan this talk to be, it was meant to be the first talk, so it's meant to be more of an introduction. Um, but because I thought people were going to give the details, I was going to give a little bit of a general overview about why and the surfaces and interfaces matter. And as you've heard, probably in the last day and a half, they're relevant in all these different heat and mass transfer applications, which are really ubiquitous, from anything in interfacial flow, wicking, droplets and sprays I'm going to talk a bit about today, evaporation and condensation, even solidification, which I'm not sure any talks on that, but on the previous talk, when that question was about can you go the other way, certainly ultrasound is shown to induce nucleation going from a liquid to a solid in ice crystal formation. So maybe it works in boiling. Electroosmosis depends on the electrochemistry of the surfaces. We've worked on slurries and the slurry electrodes, even turbulence. You've all done the Moody diagram. Slip flow in superhydrophobic surfaces, even cell growth, and of course, what people don't, often talk about is even radiative heat transfer. There's metamaterials which you can control the frequency of emitted thermal radiation. I'll skip through this because again, I thought this was going to be one of the first talks about what surface tension and what contact angle is. And what I'll just highlight here is this is apparent contact angle. When you put a drop on a surface, you're measuring not the fundamental contact angle, and you'll see in the next slide, but an apparent contact angle, which is still very important, but it's it's a little bit different. And of course, the other property that is very important in two liquid or two fluid interfacial systems are the surface tension. Everything from water is the highest, liquid, apart from liquid metals. If you're on really, really high surface tension, go to liquid metals, great heat transfer fluids, but maybe not great to use in large scales. And if you want a dielectric fluid, useful in some applications, but you've got to realise that the interfacial tension is much smaller than other traditional liquids. So when I talked about contact angle, you're probably all, a lot of you might be using algorithms to automatically measure the contact angle of, let's say, a sessile droplet on the surface. And this is an example of some of my students' work when we've been looking at the evaporation rate of droplets on a surface. This is probably 1 millimetre or 2 millimetre diameter, this droplet. And you can see here we fit a circle to that. It's all automatically done in some algorithms in MATLAB or Python. And you can see very close to the surface, although we've fitted that, we can get an apparent contact angle given by this blue theta. You can see these funny distortions of the surface here due to surface heterogeneity. If you look at a speed up, this is a video of a sped up, well, it's actually not sped up. This is sessile droplet evaporating. There's no external flow. We put a few fluorescent particles inside. We've just cut bits and pieces out of evaporating, so there's some jumps. But you'll see the contact angle even changes as it's evaporating. It's meant to be a smooth surface. I think that was PDMS. So it shouldn't be heterogeneous, but you can see the contact angles getting smaller and smaller until the end. It's almost wetting. And you might have seen that internal flow as well, which is Marangoni flow, which occurs through a variety of reasons, with some thermal, mainly thermal reasons. The surface tension change with thermal. So if we look at a microscopic view of that interface, there's always this little liquid core here with this liquid film, which is on a very small, very, very small length scale, 0.1 to 1 micron, but we can't really pick up here. We can pick up maybe 100 microns, 50 microns, but we can't pick up that. So that microscopic view of that interface of even a sessile droplet or even a spreading droplet changes that real contact angle, which is important in some things like I'm sure Professor Stefan might have talked about in his talk, or some other people. So it's just something to be aware of. But the macroscopic contact angle gives you a good idea of the overall surface properties. Of course, there's receding and advancing as well. When we're talking about just wettability, it has a big impact, and you'll see, but on the fluid dynamics and the heat transfer. But one of the good things is we can control it. We can control it with electrowetting, and I think Evelyn's Wang group showed electrowetting nuclear boiling. Actually, can turn it on and off a few years ago. You've even got photo switching, going from completely super hydrophobic almost to completely hydrophilic by turning on that field. So it just wicks into those surfaces. And there's even mechanical switching, where you can, due to the fibre structure, you can bend a surface and it can again go from super hydrophobic to super hydrophilic. It means you can control the dynamics and you control the heat transfer if you want to. So when we talk about structured surfaces, in heat transfer systems, you'll be generally dealing with a variety of surfaces depending on the process. It could be stainless steel if it's a high temperature process. So people have developed various mechanisms from, and that structured surface, or enhanced surface, it can be structured or non-structured. Here's some examples of electrochemical etching with stainless steel. Dip coating, you can get some interesting structures. You can do sintering on copper with some very fine particles. You can do a combination of photolithography by getting very regular patterns on a small scale, and then you can combine that with nanoscale features to get really super hydrophobic surfaces by having hydrothermal growth. This is a silicon etched standard processing, probably the Bosch technique, and then you can grow some zinc oxide and nanowires on there. So you could, so that's on a small scale. If you've got a bigger scale, you can do standard machining techniques like milling or electric discharging, and you can make copper fins, pyramids and slots, etc. And that scale is on the millimetre scale. And those scales affect the processes, what's happening, and all those processes, because it's such a large length scale, you can control just about all those processes from that very thin film, like I showed the difference between the apparent contact angle and the actual contact angle on this nanoscale, right up to this large scale, which can affect the whole area and the fluid mechanics. Why heat transfer? And again, this is a slide I like to use, and I grabbed it from the late Avi Bar Cohen when he gave that talk, and I just modified it a little bit at the 2014 heat transfer conference. But we're still dealing with this. Not much has changed. We've still got these. This could have even gone up a little bit in terms of the heat flux we need to remove in certain processes, the temperature on the x-axis, and how high these really are compared to the surface of the sun, albeit at lower temperatures. So we're getting to very high heat fluxes, which we'll see in the next slide. We're starting to be at the limit to standard heat flux techniques, standard heat transfer techniques. And this here is the world record of concentrating solar that was done. It was presented in a Nature paper by Roland Winston in the late 80s and hasn't been beaten, but it's still, imagine that concentrating sunlight as much as you can, you're still up to only about 1,000 watts per centimetre squared. We're getting higher than that. So if you look at methods which give the highest heat transfer rate, again, there's a broad range here because this is a generalisation. But if you look at these, probably the four highest heat transfer rates, spray cooling is probably right up there. And I've looked at literature. Maybe other people have found something higher, but the highest one I found in the literature, heat transfer coefficient, we're saying heat transfer coefficient, so it's independent almost of the temperature difference, was 77 watts per centimetre squared per Kelvin, and that was 10 years ago, or more than 10 years ago, and that was a mixture of spray with impinging jet, and I think it had an air, it could have been confined with an air jet as well. So you combine sprays with boiling, and you get very, very high heat transfer rates, and they were limited only by their apparatus to 500 watts per centimetre squared, just as was their experimental limitation. But at those heat transfer coefficients, it's very high. That was double. DARPA had the Piranha, they had an aim, they had a target, and it was double their Piranha pin fin, which they came up with after many, many years of research. So if we look at sprays as one offering some of the highest heat transfer rates, and people have studied this, a model for a spray as a single droplet. And what I've plotted here is what we're calling the complexity pathway, going from a single droplet all the way to the complex spray. So going from that, we can do successive droplets, because a spray, we go to this side, a spray is multiple droplets, multiple sizes, multiple speeds, going in different directions, hitting a surface sometimes and hitting another liquid droplet, hitting a film, bouncing off. It's such a complex phenomena, and this is where we only start. And sometimes we can't move directly from here to here without doing some of the research in what happens when their droplets are interacting. Okay, so let's start at that single droplet and see what we've learned. Again, just by changing the contact angle, this is a very thin layer of the same droplet hitting the surface, and by having a 1 micron layer on top of this little glass, which is calcium fluoride, you completely change the macro scale fluid dynamics. So that's just the contact angle, not the roughness particularly on this, not any surface structuring, simply the contact angle. Without a coating, it lands on the surface and sticks. With a coating, it bounces off. And with the hydrophilic coating, it wets and it's got a much higher spreading ratio. So over the years, if you've got a droplet impacting a surface, how can you measure the heat transfer rate? It's related to temperature, obviously. So over the years, we've worked on various methods with some of the people who are sitting there in the room, mainly Stefan and Axel Zilaf. So the way we started was that previous experiment. We got calcium fluoride. We wrapped the heater around the side, and we used an IR camera to look at that interface between the top of the calcium fluoride, which is transparent to the IR, and that water. I'll talk a bit more about that. You can have a thin foil, heat that foil and have a high emissivity coating on the back. You want the high emissivity so you can calibrate your infrared camera, and that foil can be the substrate and the heater. You could do it on silicon wafer a similar way, and we've done hot air convection heating on that, and we have a thermocouple to calibrate that as well. Silicon's also slightly transparent to infrared, but we put a high emissivity coating there. What I'll talk about later is we've used very thin thermocouples heated with a hot plate, and heat flux sensors, very fine heat flux sensors. Finally, and this is what is done at Darmstadt a lot, you have a substrate with a thin chromium nitride is a high emissivity, and a thin film chromium heater, which actually is quite accurate. And you eliminate the problems associated with looking into a semi-transparent material. So the visual work we did, this is what it looks like from below. We've got an infrared camera hitting a surface of calcium fluoride where we can see through into that interface, and we've got simultaneous measurements with a high-speed camera. So it's this method here. And this is the type of information you can get. So you've got simultaneous images of the size of side view of the droplet shape, and from below you're measuring some kind of temperature. From those, you can make some inference on here. I haven't talked about the actual heat flux because it's a little bit complicated how you can calculate the heat flux when you're looking into a thin layer of water and you're not sure how thin that layer is. But an overall idea is this showed that obviously a hydrophilic coating, you get a larger area, a larger wetting area, bigger spreading diameter, and it stays on the surface, so you get a higher cooling effectiveness of just how much heat was sucked out relative to the highest possible heat transfer rate, which is all that droplet was converted to the temperature, the surface temperature from the initial temperature. So the superhydrophobic surface bounces off the surface, and therefore it doesn't have the highest heat transfer rate, and there's an air gap between there. So let's zoom up on that a little bit, what might be happening. So here's a droplet spreading on a hot surface, and there's going to be a velocity boundary layer, a momentum boundary layer, and there's a temperature boundary layer. And if it's super hydrophobic, there might be also an interface of air and that liquid as well. So you're looking at something through the infrared camera at some kind of temperature in this liquid interface. If you look at the wavelength of a standard the sensitivity, spectral sensitivity of a standard 3 to 5 micron infrared camera, it looks something like this. it peaks at about 4.5 micron. If you look at the absorption of water, it drops down. The absorption coefficient goes down about there. So if you do a basic calculation, you're probably looking at an average temperature in about 50 micron thick layer of that water. You've got, and if you do the calculation, a rough calculation of the thermal boundary layer, it probably is about 50 microns. So you're looking at some kind of average temperature in this thermal boundary layer. So it means the uncertainties are very, very high. You can do some basic ray tracing or some more complicated systems. And thank you to Axel Zilaf, who came and spent time in the lab building this very nice system on developing a method to measure the effect of using IR temperature measurements in a semi-transparent material. So we went away from a liquid. We did some fundamental work on a semi-transparent glass substrate, so we could control everything, the temperature gradient in there. We did some interesting work on that. So the moral of the story is you have to be very, very careful when you're doing IR measurements through semi-transparent material. Okay, so I showed you the effect on the macro scale fluid dynamics simply by changing the contact angle, not the surface structure. So let's go the other way. And what if we keep the fundamental contact angle the same on these surfaces and literally just change the surface structure? You can see again, it changes the macro scale fluid dynamics of this 2 millimeter droplet from going from 5.5 by 5 micron to a 20 by 20 micron. The 20 by 20 it's almost super hydrophobic. It almost bounces off the surface. We can calculate the heat transfer rates, and I'll show you how we did that in the next coming up. But it certainly has a fundamental effect on the heat transfer rates as well, moving from, this was just a flat silicon surface, a flat titanium surface. Well, this is silicon with a titanium coating on it, just to make it a little bit hydrophobic. But just going from the 10 by 50 micron one, it gives almost, it's a double the heat transfer rate from all the other ones. And that's because it's a very complex interaction I'll talk about between the added surface area, the droplet confinement, the wicking in there, and various other phenomena which are all affected by these different scales. So if we look at a simple experiment of droplet impingement on a surface thermocouple, again, this experiment, we just can put a single droplet on a very, very thin surface thermocouple, have a high-speed data logger, which goes about 2 kilohertz, so we can pick up that transient process. And again, you're not measuring heat flux, you're measuring temperature. So how do you turn that into a heat flux? If you zoom up on that surface thermocouple, it's about 130 microns thick. We know what the polymer is made of. We know the conductivity. We know the actual thermoelectric elements, where they're sitting in there. It's about the middle. So we can use a classical integral transform technique to solve the 1D conduction equation with two boundary conditions. We know the temperature in the middle, and we'd also know the surface temperature we've measured in another way. And we can solve that. We fit our data, and we get this fitting function, and you can see how it matches the data well, and then we can calculate the heat transfer rate, the heat flux. So given that method, we're going to see what happens with successive droplets hitting each other on either a hydrophilic surface or a superhydrophobic surface. You saw previously that we showed the superhydrophobic surface bounced off and the heat transfer rate on the calcium fluoride looked a lot less. We want to see what happens when you have multiple droplets. So if we look at this uncoated surface thermocouple, the contact angle is about 65. We coated it with a superhydrophobic coating and brought it up to about 152 degrees, which is superhydrophobic. We had similar Weber numbers, and hopefully people have talked about Weber numbers, and you know what a Weber number is. It's just the ratio of the terms of the inertia and the surface tension of the droplet, so how fast it's going if everything else is constant. And we had a droplet hitting the surface and spreading, and then as it starts to recoil, another droplet comes in and hits it, and then we have a third droplet coming in onto the coalesced droplet. The super hydrophobic one, that droplet comes in, bounces off, and the next droplet comes in. And it's on a slight angle, so we didn't have the first droplet bouncing up and hitting the second droplet, interfering with it. If you look at the spreading diameter, this is a non-dimensional spreading diameter. The maximum, we have the first droplet spreading, the second one, it coalesces, gets a bit bigger, the third one, and then it basically reaches a limit because eventually the surface tension is not going to hold it in, it's just going to form a film and drain. So it reaches a maximum. And obviously the super hydrophobic one, it hits there, bounces off. The next one, there should be no difference because it's always hitting a fresh surface. So if we look at the heat transfer rates, again, here's the actual heat transfer rate as a function of time in watts. And here's the first one coming in. The second one's now hitting another droplet and coalesces, and it's not hitting a fresh surface, so it goes down. And eventually the third droplet, it gets even lower. But as you would expect, there's no difference in the heat transfer rate for the super hydrophobic surface because it's hitting a fresh surface. They should be identical. So what this comes out as now, if you look at the integrated energy now, how much energy is being taken out of the surface by integrating this as a function of time, then you see that every time that droplet hits, it's taking out less energy. So you come to a maximum as well, just hits this film, it stays on there, it's hydrophilic, and eventually it might drain. But you're always going to hit some kind of liquid film, so that it starts to increase much more slowly. On the other hand, each time the super hydrophobic surface is exposed, the droplet takes out less energy. You can see here 1.2 to 6 or so, but it continues on. So then your next assumption is, well, if we've got thousands and thousands of droplets coming on here on the super hydrophobic surface, maybe the net heat transfer you can take out is higher. So then we go, that was two droplets on top of each other, multiple droplets. The next pathway to complexity towards a spray is having two droplets coming in and spreading and interacting as they spread. So this is a little bit of a tricky experiment. We had three scenarios, two droplets coming in there, and the first scenario is when they're spreading and interacting, and they're both spreading. One's recoiling when we've got a delta T of 16 or 17 milliseconds. One's recoiling, the other one is spreading towards it, and the third one is almost stationary, it's almost sessile, and the second droplet interacts. We had a separation between these two to make sure that there was some interaction between the two droplets, but not really, really close, but enough that I think it was about almost a diameter of interaction on the maximum spreading. So here's some of the high-speed images taken, but just to highlight some of the key points about this is when they're impacting and spreading together, you get this upwelling sheet associated with momentum transfer as they hit, going vertically, and you might even lose this uprising sheet. You might even lose some of the liquid from the surface. You might form secondary droplets. That's when it's almost simultaneous, up to 1.5 milliseconds. If the second one is recoiling already if the first one's recoiling when the second one impacts, you get a little bit of this instability, but you don't get this uprising sheet, and there's not much difference when it's sessile, when it's almost stopped, and you have that secondary droplet impacting and spreading onto it. Because of time, I'm not going to talk about the spreading diameter, but the overall summary of this is that it turns out that interaction, so here is, this one is a single droplet, so this star, and if you double that, that would just be two droplets spreading and not interacting at all. So that is, doubling that it turns out to be the best case. So that would just be two droplets spreading, which is this screen, taking the distance to infinity and not interacting at all. That's the red one. Nothing else. When they were interacting, it was close when they were spreading, but it didn't even get to the non-interacting droplets at all. So that tells a story that you don't really want them interacting, because that interacting starts to mix up the cooler fluid with the hot fluid and take some of that energy out. All right, so we're getting some design criteria. I know Professor Tropia, I was interested in listening to his talk, which I couldn't, about designing spray cooling systems. So maybe I'll get those slides, but I'd be interested to hear what you had to say talking to you directly here. So we've got droplets going everywhere, and we had a good look at the literature and to see if there's any correlation between the different structures that people have done when done enhanced surfaces from nano, micro, milli, the hybrid structures like I showed you on that mixture of the pillar, the micron-sized pillars with the zinc oxide nanowires, the mass flux, and of course the temperature of the surface compared to the boiling temperature, which is T surface minus T sat. So this black line here is the left of this is single phase, and this is all boiling. And if you look at this, there doesn't seem to be any major correlation. Otherwise, it goes up a little bit here, but it's there's no correlation. So that's the holy grail. Maybe a mixture of this acoustics, which I just heard, might be able to give some more information on this process. So when you're doing spray cooling, of course, you need to understand the sprays that you're talking about, that you're using, and we use standard Doppler anemometry to get the droplet distribution. And again, this is a pretty standard way to measure the heat flux on when you've got spray cooling. And remember, this on spray cooling, you're taking a lot of heat out, so it's much easier to get the heat flux than on a single droplet. You just have two thermocouples at a known distance, or two temperature sensors at a known distance, and you can calculate the heat flux. And you can focus that heat in by changing diameter and insulating everything. We looked at different surfaces and various Weber numbers associated with those droplets. And again, spray cooling is known to have high heat transfer rates per amount of liquid you use, but you don't have a continuous flow. If you look at the differences here between this is just a smooth copper surface, we've zoomed up, and you can see here the droplets are hitting a mixture of, sometimes the surface is being cleared, sometimes this is not even boiling. There's no boiling associated with this. It's just a non-boiling below the saturation temperature. But you've got a lot of things happening here, droplets crowning on the liquid film, some droplets interacting with others coming in. But most of the time, it's not really hitting a surface. If I go here, straight on the surface, it's the super hydrophobic surface. You can see here, the droplets are actually smashing on the surface and then bouncing off and breaking up and creating almost a vapor film of really tiny droplets across the surface. So that has a big difference. There's problems with the super hydrophobic surface, which I'll talk about in a sec. So we looked at various surfaces and again, this is not done by any intelligent design. This is done by looking at literature and making some assumptions, but there's no physics associated with the size of these. But now we're probably up to the stage where we can do that, which would be the next level. We did various copper surface where we smoothed it, we roughed it up, then we put some machined roughness in at different sizes, and even did golf ball types of patterning to see the effect it had on the overall heat transfer rate. And as expected, it did, and it's significant. And this is only on a micro, sort of a micro scale. You can see here's the smooth. The smooth one is the red. This is the heat flux as a temperature, and this is all non-boiling. I'm not going to present the boiling stuff here because we're still going through some of the data, but this is all non-boiling, and it turns out that the 200 micron surface is the best by a long way. At the same surface temperature, if you look at here compared to, let's say, the golf ball, at the same surface temperature, you're getting almost a 50% increase in the heat flux. And again, like I said, that's not optimized. There's a lot of room for improvement. So where did that surface sit on this little diagram here? Again, we were very, very low temperatures and very low flow rates, only 3 to 6 kilograms per metre squared, and we're already up there with no optimisation, just it's almost arbitrary features on that. So there's a long way to go, and even past these type of values. The final thing that I wanted to say was we talk about this, changing surfaces, putting coatings on to improve wettability or to improve the structure, to improve wetting or wicking, etc. But what happens in the long term? So we ran some experiments for 36 hours, keeping the spray on continuously, and even that wasn't so easy. But this is some examples of what happens to surfaces, and these are metal surfaces. Silicon, which are harder, we haven't tried silicon yet, but here's a copper surface before it was polished, and after 36 hours, it obviously went oxidized a little bit, and it looks quite different. And we've done work, you'll see the next slide. We've done some SEM imaging, etc. SEM imaging, showing that it changed the surface structure. Here's a super hydrophobic surface which had a chemical coating, which was a copper silver, a sort of alloy, which was coated on the surface, which made it super hydrophobic. You can see you can see the coating on the surface. After 36 hours, almost nothing left on there. In fact, that when we measured it, it was the spray probably after 5 minutes, it was wiped off. Even the commercial Never Wet, which is meant to be very robust and you can spray it onto your clothes, that didn't last more than 10 minutes either. So this was after 36 hours, the surface was essentially removed. You'll see that in the next slide. This is the static contact angle or apparent contact angle before we started and after 36 hours. And the contact angle went down considerably in the smooth copper. Aluminium was less sensitive. Apart from the rough aluminium, it reduced the contact angle. Any of the super hydrophobic coatings we used, we tried other ones, they get wiped off. So there has to be a more robust way of doing that. So they lose their super hydrophobicity completely. Raw aluminium didn't change much significantly at all. The roughness we looked at as well. And after 36 hours, this is a relative roughness. So it doubled. This 2 means the roughness doubled over that. There wasn't much of a change for some of the surfaces apart from this smooth copper. So this is why the contact angle went down. It's hydrophilic, you make it a bit rougher, and it wants to wet the surface a bit more. So that's something to look at when you're designing long-term, more practical spray cooling applications. So just to summarise then, this is good because I've got to get going in a sec. These different sizes, and I hadn't finished. I've adapted this from a recent review paper. This is not mine, but I've adapted it a little bit. But it's a really nice paper, and I forgot to put that in. It gives you the major physics associated with structuring or tailoring the surface at different scales, from boiling enhancement by letting bubble nucleation be more efficient, from wickability enhancement to wick and re-wet the surface after it evaporates. Flow confinement, that's what's happening on those different structured surfaces I showed in the silicon. Area enhancement, that's a big one where you've got a much higher heat transfer area once you structure a surface. That triple contact line length, I haven't talked about it much, but I think there might have been other talks in that area, in that field, on this workshop. And the contact angle. The contact angle changes the fluid dynamics, and it can, no matter what structure, no matter the size of that underlying structure of the surface. So that summarises that. So that's an incredibly important one. And finally, just acknowledgements with the PhD students and the people involved in this research over the years, including Axel and Peter. So thank you. And that I quickly did an AI-generated image of droplet boiling enhancement, droplet boiling on a structured surface. It looks okay. Thank you. I probably don't have time for questions. I'm sorry.
Okay, we understand that, Gary, because we will start. So if there are any questions, maybe they can email you in person later on.
Yeah, that would be good.
So So thank.
So I welcome any questions.
So thank you once again, Gary, and we will.
Thank you.
Thank you.
Thank you.